Last time we focused on one particular type of polynomial function, namely the quadratic function, which is a second degree polynomial. So now we're going to talk more generally about polynomials. So one of the things you should be able to recognize immediately when you look at a polynomial is the end behavior. And by end behavior, I mean what happens to the graph of this function as you move to the left or as you move to the right. Will the graph be rising or falling? So let's say we have a function f of x, and it's defined as a sub n, which is just a number, times x to the nth power, plus a sub n minus 1, another constant, times x to the n minus 1 power, etc., all the way down to a sub 0. So what we want to focus on is the power of n, right there. So, and if it's not in descending order, then rearrange it, or at least pick out the term that has the highest degree power. Now, if that highest degree power is odd, like let's say x to the third, or x to the fifth, or x to the ninth, or x to the first, I guess, then we have two possibilities. And what we need to look at is the coefficient in front of that x to the nth power. And if that coefficient is positive, then that tells me that my function will fall to the left and rise to the right. A typical example for that. So now this is when n is odd. So let's say, for example, we could look at x cubed. An x cubed graph looks like that. And so if the coefficient in front of x cubed is positive, the graph will fall. And let me put a little point on here. As we are moved to the left, the graph is falling. And as we move to the right, the graph is rising. So we're talking about the end behavior. So I know inside here, well, yeah, it's rising, and then it's falling, and then it's rising again. But just looking as we keep going. So as x gets really, really big, where is it going? It's going up. And as x gets really, really small, negative 100, negative 1,000, where is it going? It's going down. Now, on the other hand, if that leading coefficient right here, this a sub n, is less than 0, if it's negative, then the opposite's going to happen. So let me give you an example. And it doesn't have to be a cubed, it could be any graph. So, for example, it could look something like this. Okay. And so this is saying that our degree is odd, like x to the fifth or x to the seventh. If the degree is odd and the leading coefficient is negative, then that tells me that as x gets really, really big, my graph is falling to the right. Oops, where's that point? There it is. The graph is falling to the right. And then as x gets really small, like really small negative, moving towards negative infinity, my graph will be rising. So it rises to the left. This point doesn't want to stay. It rises to the left, and it falls to the right. All right, so those are the two different scenarios. Now, what if, on the other hand, instead of n being odd, what if n is even? So if n is even, we also have the two cases. We have to look at that leading coefficient. And if the leading coefficient is positive, then our graph will rise to the left and rise to the right. For example, just look at a y equal x squared graph. Rises to the left, rises to the right. If that leading coefficient is negative, this is for an even-powered polynomial, the highest degree is even number, then we might have something that looks like this. Then our graph will fall as we go far to the left, and it'll fall as we go far to the right. All right, so let's look at an example just to make sure you understand this, because it really is a pretty easy concept, although with all the writing and words, it seems like it's more complicated. All right, describe the end behavior of the graph. Well, first of all, let's identify. It's an odd power. So the highest degree is an odd number. And then we look at the leading coefficient, and that's a positive value. So that tells me, and you can look at the chart if you need to. We have odd and positive, that's the first case, falls to the left, rises to the right. And so that's our answer. Falls to the left, rises to the right. And that's it. That's all you need to know. So if you can remember y equal x cubed and y equal x squared, and what happens with those, and then if you put a negative in front of them, that basically will tell you everything you need to know. Y equals x cubed, y equals negative x cubed, y equals positive x squared, y equals negative x squared. So if you can remember what those graphs are, and then looking at a particular problem, this is an x cubed, and it's a positive coefficient, so it's going to be like this one. So it falls to the left, rises to the right, and that's it. All right, so let's move on. How about the zeros of a polynomial? Now, I've mentioned already, the zeros of our function are the x-intercepts, and sometimes they're referred to as the roots. So all of those terms, zeros, x-intercepts, roots, all mean the same thing. Where does the graph cross the x-axis? If c is a zero of a function f, then x minus c is a factor of the function, and f of c is going to equal 0. I'm going to jump right into some examples for this. Find the zeros of g of x. All right, so I want to know, let's give you a visual. I'm looking for the x-intercepts. Well, what are the coordinates of any point on the x-axis? It's always going to be something comma 0. So the y value is 0. So my function value is 0. So essentially when I say find the zeros, I'm asking you to solve this. Now, one of the techniques we used with quadratics was we would factor if possible. So what can I do here? Well, I can factor an x out of every term. So this would become x squared, x to the first, minus 2. And now I have a quadratic, and we know how to factor those into two binomials, x, x, and then multiplies to negative 2, adds to negative 1. So now I have everything factored. So I'm multiplying three different things. So that means either x is equal to 0, or the x minus 2 is equal to 0, or the x plus 1 would have to equal 0. And in those cases, I get x equals 0, or x equals 2, or x equals negative 1. And so those are my zeros of this function. And if you list it, by the way, if you just wrote them all like this, that would be fine as well. Those are all the zeros. So notice, x equals, let's say here, x equals 2 is a zero of this function. That means that x minus 2 has to be one of the factors. And if x equals negative 1 is a zero of my function, that means x plus 1 has to be one of the factors. And if x equals 0, that means x minus 0, or just x, also has to be a factor. So if I give you the zeros, you can tell me what the factors are. And if I give you the factors, or if you're able to factor a polynomial function, then you can tell me what the zeros are. Find the x-intercepts of this function. Okay, so it sounds like the same idea. We're just using the term x-intercepts instead of zeros, but that means the same thing. We're setting this function equal to 0, and we're trying to solve. So the first thing we try and do is say, can we factor this? And not every term has an x, at least an x to the first power in it. And not every term has a common factor. 13 is a prime number, so no, there's no number I could factor out of all of these. The next thought is, well, maybe factor by grouping. You know, that was something you learned back in algebra. So I could factor out an x squared from the first two terms, and I'd have 4x plus 13. And then I could factor a 4 out of that, and I'd have x minus 3, but that doesn't help. And so all of a sudden we're stuck. If this was a quadratic, we have a quadratic formula, but this is a cubic. We don't have a cubic formula. So we're going to spend some time later in the course learning some techniques to help us find some of these factors. But for now, if we can't factor it, what we're going to have to do is go to a calculator and look at the graph. So let's put 4x to the third plus 13x squared plus 4x minus 12. Let's move this over a little bit. There we go. 4x cubed plus 13x squared plus 4x minus 12. Zoom 6, standard window. Aha. It looks like we have an x-intercept at -2 and then maybe at +1. I'm going to hit trace, type -2. Sure enough. Okay. And then at 1. Yep, looks like that. Now, I could go to the calculate menu by pressing second trace, and I could find the zeros, or the x-intercepts, number 2. And then I have to go through, we've talked about this before, find a left bound. So if I go to the left of z0, enter. Go to the right, enter. Give a guess, enter. It says 0.75. So I'm sorry, when I hit trace and I pressed 1, it didn't actually give me the 0, did it? No. So 0.75 was the other 0. Once again, we go through that second trace, number 2, left bound, enter, right bound, enter, guess, enter. X equals 0.75, that's when y is equal to 0. So it looks like it happens at -2. And you can see if I go to the left of -2, it goes underneath. And if I go to the right of -2, it goes underneath again. So it looks like it never crosses the x-axis at -2. And so I only have 2 x-intercepts, even though it's an x to the third power. And so here's what happens in that case. It turns out, so we have, let's write x equals -2, and then we also have x equals 3/4. So I automatically know that x plus 2 is one of the factors of this function. And x equals 3/4, or if I multiply both sides by 4, I get 4x equals 3, and therefore 4x minus 3 would equal 0. Some people would just write, well, can't I just say x equal, or x minus 3/4? Yeah, but when we're factoring, we usually don't leave it as fractions. So this would be okay, but know that that's usually what you're going to see. So we want to write it without a fraction. All right, but that's only going to give us an x squared. Well, it turns out that when a graph bounces off like that, x equals -2 is actually a root twice, or a double root, or a root of multiplicity 2. So it turns out that we could factor, well, let's just erase the whole thing here and start over. We could factor h of x as x plus 2 times x plus 2 times 4x minus 3. That's the factored form of that. So we need to use the calculator to find the roots. It says find the x-intercepts. So we are done right here. We used our calculator and we're done. But I'm working backwards now from the answers to show you what the factored form would look like. And if you multiply this out, if I multiply the first two, I'm going to get x squared plus 4x plus 4. And then if I multiply that times 4x minus 3, and I'm going to do x squared times 4x would be 4x to the third. And then x squared times -3 is -3x squared. and now do the 4x times each of those. That's going to give me 16x squared minus 12x, and then multiply the 4 times both of those, plus 16x minus 12. And when I combine my like terms, I'm going to get a 4x cubed, check. I have a negative 3x squared plus 16x squared, which would give me 13x squared, check. Negative 12x plus 16x is a positive 4x, and then minus 12. So I multiplied to show you that this indeed was the factored form. So when we have the, let me go up here. When we have a factor occur more than once, we say that in this case x equals negative 2 is a 0 or an x-intercept of multiplicity 2. Multiplicity 2. Okay, if it occurred 3 times, if we had a higher polynomial and we had factored to x plus 2, x plus 2, x plus 2, then we would have x equals negative 2 as a root of multiplicity 3, etc. And it turns out when that multiplicity is an even number, on the graph it'll bounce off the x-axis, it won't go through it. All right, so what if I asked you, find a polynomial function with zeros, negative 2, negative 1, 1, and 2? Well, that should be easy enough. We'll call it f of x. And if one of the zeros is negative 2, that means x plus 2 is a factor, because when you set that equal to 0, you get x equals negative 2. And then x plus 1 would be a factor for the negative 1. And then x minus 1 for the 1. And x minus 2 for the 2. So it didn't say to multiply it out, so that would be our answer. If they did ask us to multiply this out, I think I'd want to rearrange it a little bit. I would do the x plus 2 times x minus 2 together, because that's easier to multiply, and the x plus 1 and the x minus 1 together. And so now I have the difference of 2 squares, so that's just going to be x squared minus 4. For those two, the middle terms cancel out. And then same thing here, that's going to be x squared minus 1. And now that's easier to multiply those together. So when I distribute or FOIL, I'm going to get an x to the 4th. And then I'm going to get a negative x squared and a negative 4x squared, which is going to give me negative 5x squared after I combine those. And then a positive 4. So if they ask you to not write it in factored form, you would then multiply all those factors out and get your answer. Okay, problem set starts on page 109.